Okay, so we're going to look at prime factorizations instead of lists here. And I'm just going to use 18 and 12, or 12 and 18. So we're going to do a tree to make a prime factorization. So 2 goes into 12 6 times, and 2 goes into 6 3 times. So 12 is 2 squared times 3. And then similar, 18 is even. So I always like to do 2 whenever possible because it's the easiest thing to divide by, besides 1. 9 times, and 3 goes into 9 3 times, and we know we're done with the prime factorization tree because we have primes at the ends. And so the prime factorization of 18 is going to be 2 times 3 squared. And I've mentioned a couple of times now that for the greatest common factor for prime factorization, what we do is we take the lowest power of common primes. So for the numbers I have here, they have a 2 as a prime factor in common, and the lowest power of 2 I see is 2 to the first, or just 2. They also have a 3 in common, and the lowest power of 3 available is a 3. So my claim then is the greatest common factor of 12 and 18 is 2 times 3, or 6. And I'm going to highlight those. Greatest common factor, I selected this 3, and I selected that 2. Now here's the cool part about the lowest common multiple. And I'm going to hold off on writing how to use the prime factors and just build it a different way. So here's the way to think about it. I'm looking for a multiple of 12. Well, if it's a multiple of 12, it's 12 times something. So that means all of 12's factors has to live in the multiple. So that multiple has to have a 2 squared times a 3 in it, because 2 squared times 3 is 12. If the 2 squared and the 3 aren't there, it ain't a multiple of 12. Next, I look at the 18. So bottom line, one technique of finding the lowest common multiple with primes is to just take the first number's prime factorization and just write it down, because you need it all. Look at the next number. The next number, 18, says I need a 2. Okay, look at the LCM we've started. Do we have a 2 already? We have more than enough 2's for 18, right? We have 2 of them. We only need 1. So I don't need any more 2's. So that's done. Check. Then I look over at the next part. Next part of 18 says you need 3 squared, 3 times 3. So I look at my factorization over here. I have a single 3. So that means I need, if this is going to be a multiple of 18, I need another 3 in there. And now I have the 2 I need right there. And I have the 3 squared that I need. So I can then say that the LCM of 12 and 18 is 2 squared times 3 squared. Okay, so again, I'm just thinking about what it means to be a multiple. That means it's a number 12 goes into, so it's 12 times something. So 12 has to go into the multiple. So that means 2 squared times 3, which is 12, has to live there. Then I look over at the second number and I check, do I have enough of that factor? Yes. Do I have enough of that factor? Not yet, so I multiplied it on. So I believe, just on the idea of what it means to be a multiple, and I want it to be the lowest multiple, sometimes we call it the least multiple, I want to have it as few factors as possible. So I don't need any extra 2's, I did need that extra 3, and that's it. Now, if I compare these factors that I have here, the 2 squared, so let's use a highlighter of a different color. Let's take red this time. That 2 squared, well, you could say that's this factor right here. And the 3 squared is that factor right there. So now I'm wondering, is it a coincidence that the greatest common factor selected these two factors and the lowest common multiple selected whatever was left? Does that always happen? Interesting. So if it is true, then I got to come up with a statement kind of like I did above. So before I make that statement, I want to do another example. And I'm going to pick on the problem we worked on a moment ago. Let's work with 90 and 84 since we have the prime factorizations right here. A new page. At this side, hang on. Come on, Noel, get in here. There you go. All right, math on a snow day. Oops. Let's switch back to the pen. So we've got 90, and earlier we found the prime factorization of 90 was 2 times 3 squared times 5. And then we had 84, and we found that 84 was 2 squared times 3 times 7. 2 squared times 3 times 7. And we've done a few examples now with the greatest common factor. And the greatest common factor chooses the lowest power of the common primes. So if we look here, what primes are common? 2 and 3 are common. And the lowest power of each, let's keep this color consistent. Go with yellow, is 2 to the first and 3 to the first. And we did it a couple of different ways earlier and found the greatest common factor was indeed 2 times 3 or 6. Lowest common multiple or least common multiple. So I was wondering, based on the example back here, if the lowest common multiple are the factors, the prime factors that the GCF didn't select. And then we'll try to make sense of that. So we'll do this in a couple of different ways. So first, we're just going to guess. The GCF didn't select that 2 squared there. It didn't select the 3 squared there. Didn't select the 5, and it didn't select the 7. So I'm guessing that that multiplication, I'm going to whip out a calculator. I wrote something wrong. That should be a 3. That multiplication right there should be the lowest common multiple of 90 and 84. So I think I'd like a calculator for that. Go. So we've got 2 squared times 3 squared times 5 times 7. So 1260 seems to be the smallest number that 90 and 84 go into. All right, 1260. So I think that's the least common multiple. So now I'm going to do it with the other method by building it. So this is my build with primes method. And the build with primes method, you basically pick a number and write down all of its factors, right? I'm looking for a multiple of 90. So that means all of 90 must be in that multiple, which is 2 times 3 squared times 5, right? So that's step 1 of finding my multiple. Step 2 is to look at the other number, 84. So 84 says I need a 2 squared. So I look at what I have, don't quite have that. So for 84, I'm going to have to multiply it by another 2 to get a 2 squared. 84 says I need 1 3. I look down here, I got plenty of 3s. I don't need any more, right? I need any more. Well, I'm looking for the lowest of the common multiples, so we don't want any extra. Then I look over at the 7, and there is no 7 down here at all, so I got to multiply it in. All right, so clean that up a little bit. If I put it all together as a prime factorization, that would be 2 2's, so 2 squared, times 3 squared, times 5, times 7, which happens to be what I have above. Let's just think about whether this makes sense. So thinking about 90, let's use green to talk about 90. 90 says it has to have a 2. and a 3 squared, and a 5. So 90 is happy. That's a multiple of 90 for sure. I have an extra 2 and a 7, right? So what does that tell me? That this number right here is 90 times that extra 2 times 7, which would be 90 times 14. Let's use red to talk about, or blue maybe, to talk about 84. So 84 says I need a 2 squared. Got it. 84 says I need a 3. I got more than enough. I'm good there. And I need a 7. Got it. So this number is definitely a multiple of 84. And I can see that it's 84 times the extra 3 and the 5. 3 times 5 is 15. Let's double check to see if this works. So I want to double check. What is 90 times 14? What is 84 times 15? And it should be, if all works out, 1260. So 90 times 14 and 84 times 15. Cool. I think I did it. I found the multiple of 90. That's also a multiple of 84. So I definitely satisfied the common multiple idea. The next question is it really the lowest possible common multiple? Well, if it's not the lowest, then I could pull out any one of these factors, or at least one of them. So let's see, could we afford to take away a 2 out of there? Well, if we took away one of those 2's, then 84 is going to scream foul. So I can't mess with the 2's. Can I take a 3 out of there? 90 says, I got to have a 3 squared. Okay, I can't mess with the 3's. And I pull a 5 out. There's only one 5. 90 says it needs it. Can't touch it. 7. There's only one 7. 84 says it needs it. So I can't touch any of those factors. If I get rid of any one of them, either 90 or 84 won't work as being a factor in it being the multiple. So it looks like 1260 is the lowest common multiple of 90 and 84, which coincidentally, like last time, turns out to be the stuff the GCF did not select. Okay, so what did the GCF select again? The GCF selected, from our previous work, the lowest power of the common primes. What's left over? Let's use a green highlighter. What did we use last time? Last time we used a red highlighter, okay, to identify what was left behind. The 2 squared was left behind, the 3 squared was left behind, and the 5 was left behind. And if you think about it, using a similar explanation, the LCM is going to be the highest powers of all of the primes. Not the common primes, but all of the primes there, right? So what's the highest? So the primes here are 2, 3, 5, and 7. The highest power of 2 is a 2 squared. The highest power of 3 is a 3 squared. The highest power of 5 is just 5 to the first, or 5. And the highest power of 7 available is just 7 to the first, or 7. So GCF selects the lowest power of common primes. The LCM selects the highest power of all primes in those factorizations. And these are the prime factorization techniques for greatest common factor and lowest common multiple.